How do I size the correct vortex tube cabinet cooler for my electrical cabinet? This video highlights some simple steps into sizing the correct vortex tube cooler. Step 1, you need to calculate the internal heat load. Now this heat is generated by the electrical equipment in the cabinet. The overall wattage of the heat load may be specified, we really know the equipment in there, but if it's not specified, what we typically do is assume 10% of the overall power provided to the cabinet will be generating heat. So if we've got a cabinet with 5 kilowatts of kit in there, we're assuming it'll be about 0.5 kilowatts of heat will be generated by that kit when it's being used. Next step, calculate the external heat load, the external differential. This is the temperature difference between the desired maximum temperature inside the cabinet and the external temperature in the environment. The external temperature may vary considerably depending on whether it's a hot day or a cold day, for example. We want to think about worst case scenarios here. So we think about the worst case scenario in the factory, what's the maximum temperature the ambient can get up to. If we can get up to a maximum of 40 degrees in a factory in the summer and we want to maintain the cabinet at 25 degrees or lower, then we have a delta T, a temperature difference of 50. Once we work that out, next we need to calculate the surface area of the cabinet. This is pretty straightforward, as most cabinets are basic cuboids. So you just do the surface area of all of the parts of the cabinet, add them up, and that will give you your surface area of the cabinet in meters squared. We use the heat per meter squared charts for the correct delta T. These charts are readily available, displaying one here. And this will give us a heat loss or gain per meter squared for the correct temperature difference. And then we just calculate that simply. We add the external to internal heat loads to get the overall heat load generated in the cabinet. This will be in watts. So for example, we have a 1 by 1 by 1 cube cabinet, to keep it nice and simple. We want to keep it at 20 degrees and the maximum ambient temperature will be 40 degrees. And in the cab we have 5 kilowatts of kit. So the internal heat load is 10% of the 5 kilowatts of kit, 0.5 kilowatts. Surface area is 6 meters squared. We have the 6 sides of the 1 by 1 cube. The delta T is 20 degrees, difference between 20 and 40 degrees. And then we're looking at the charts, we see we have 24.4 watts per meter squared for that delta T. So that's 0.146 kilowatts of external heat load. We add that to the internal heat load of 0.5 kilowatts, so we have a total heat load of 0.646 kilowatts. And now we just need a vortex tube with a wattage higher than this, so it can cope with that worst case scenario. So in this case, we'd suggest an 849 watt cabinet cooler, and that would easily cope with that maximum potential heat load of 0.646 kilowatts. You can use this method to size up cooling requirements for any electrical cabinet. Some people suggest that we take off one of the sides when calculating the external heat load, so the top side won't be absorbing heat. I like to keep it in, so it gives us a little bit extra leeway there, so we're getting a truly robust solution that's definitely going to be able to cope with any unexpected changes. Final point is, if the heat load is more than 849 watts, which is the biggest cooler that we produce, you can use multiple coolers in one cabinet. There's no reason why you can't do that, so that can cope with larger heat loads.